welcome to PCB Chat, where we talk with experts across the printed circuit design, manufacturing, and electronics supply chain fields. I'm Mike Buteau, Editor-in-Chief of PCD&F and Circuits Assembly. This week's podcast is sponsored by PCB Update, the digital newsletter for the electronics industry. Get all the latest technical and business news related to PCB design, fab, and assembly. Subscribe at PCBUpdate.com. This week, we continue our new series called The Screw-Ups. In these segments, we talk to experts in electronics manufacturing about specific problems they've encountered and offer up some potential solutions. My guest today is Tim O'Neill. Tim has nearly 25 years experience with solder materials, primarily with AIM Solder, where he is currently Technical Marketing Manager. And our topic today is post-soldering residue. Tim, what do you have for us?
Hi, Mike, and thanks for the opportunity. I think that the podcast is a great way to get information out to our user base and share with them the knowledge that we've accumulated over the years to help them avoid common pitfalls. Today, we're going to talk about rework and common errors and omissions made at the rework bench that lead to calls to us as the manufacturer. How can we provide a remedy or a solution to a problem? And the scenario often plays out in the following way. We'll receive a call from either an end user or contract manufacturer that's building an assembly for something. And it will either be the result of a board that's been returned from service that has demonstrated a field failure, an electrochemical field failure, specifically whether green residue, white residue, dendritic growth, or a dead short. We see the full range of these types of failures. We also often get brought into a conversation between contract manufacturers and their customers before the boards make their way into the field to address the appearance of residues post-soldering. So just to give a brief overview of what we would consider expected is that 80%, 90% of the industry globally uses no clean solders, meaning that the fluxes are formulated to be left in situ after soldering, don't require cleaning, and pass the battery of tests that are set forth to whatever specification the customer is adhering to. Most often, certainly here in North America, is the IPC-J standards, but we have the JIS standards in Asia, we have the IEC standards out of Europe, and now we're seeing even more in-house developed standards, particularly from the automotive sector, as they just cram more and more electronics into harsher and harsher environments in the automotive segment. So as you can imagine, electrochemical failures in that environment become more of an issue because we're relying on the automobile to do more things automatically, and we can't have those failures because they could potentially become life safety issues. We're transitioning to higher voltages as cars migrate from internal combustion engines to battery operated. So there's just a lot of converging factors that are making this issue more of a concern. So as flux manufacturers for solder paste, wire solder, liquid flux, we are doing deep dives into the electrochemical properties of the products. And we can formulate products that meet the mission profile of the assembly that's being built. What we can't do is we can't control how the end user applies them. And this is where we run into these types of issues. And I'll just go down the production line. In my head, the way I kind of construct the scenario, let's go down the line chronologically and see where the risks lie and why some risks are riskier than others. So we'll start at the printer where solder paste is used. Solder paste does have some risk associated with it. Whenever we're leaving a residue behind, depending upon the conditions that it's subjected to, ionic species will be present. So post-soldering, no clean flux residues from a surface mount operation are always going to be there. Solder paste today consists roughly of 50% flux by volume and 50% metal by volume. So after reflow, there's going to be a percentage of the flux that's left behind. And as such, there are ionic species that are in that actually do the fluxing portion of things. And then the flux is part of a system. Encapsulants, oxidation, degradation are all part of creating a chemistry where the residue that's left behind remains non-conductive, non-corrosive under a wide range of conditions. Basically, we apply a voltage and we stick it in high temperature and humidity to promote electrochemical growth. And with that, whether it's the IPC, the J standards, the IEC standards, or the JS standards, all of which use similar techniques, we can determine what the electrochemical properties are of solder paste. And solder paste is kind of neat because it fits into a box. The material gets printed, the components get placed, and it goes through a reflow oven. Very difficult to not process solder paste properly, meaning we're all going through a 3-minute to 5-minute reflow profile, and it's almost universal how the paste gets reflowed. So when we formulate, we know the process that the material gets exposed to. So we understand exactly the conditions that it will be processed through, and the outcomes are fairly predictable, which isn't to say that there aren't circumstances where things can go wrong, but they're much less likely to go wrong in that process. I would say that wave solder is probably wave or selective are a little less predictable because as I just mentioned, liquid fluxes can be used in a variety of different applications. In a full wave solder, for example, it can be sprayed. Some people, believe it or not, are still using foam fluxes to apply it. So the application volume can vary. It can be easily over-applied. An unskilled operator may find that increasing the volume of flux that applied to the board solves solderability issues that they're experiencing without realizing that over-applying the flux can put a lot more of these ionic components onto the board than are intended, or that correlate with the tests that were performed to establish the product as being reliable, and then you can have problems. Also, the wave solder process remains a bit of a black art. Preheat temperatures and wave solder configurations aren't as universal as they are in typical convection reflow. There's also the possibility for the use of pallets, which can introduce variability that we can't anticipate. On the wave solder, a common area of concern, for example, is pallet maintenance actually becomes a concern for electrochemical migration, because if the pallets aren't being cleaned at regularly scheduled intervals, flux can accumulate on the aperture of the pallet and become hyperconcentrated and then be transferred onto the board. So now you've got flux residue that's not on the board, it's actually on the pallet, but because the pallet's been fluxed a number of times, left uncleaned, the solvent has been evaporated, and in fact, fluxes are formulated to have strong capillary action, so the flux can wick into areas where it may not see sufficient heat exposure to be thermally degraded, and then you stick your board into a carefully machined nest, and you just simply, then there's intimate contact between the board and the pallet, and you're transferring this hyperconcentrated flux residue onto the board, which can be an issue. Also, the way the flux is applied, it can pool on the around the apertures due to the surface tension of the solvent that's used, whether it's water or alcohol in the flux. So it's got more variability than, let's say, the surface mount process. So these things can happen, and they can cause residue and reliability concerns. And like I said, I'm just kind of running down the line in my head as to where you might run into these. Some common, some not so common. These, I would say, are less common occurrences. Similarly, with selective soldering, the issue with selective soldering is that unlike a traditional full wave, in selective soldering, the heat source is localized. So if you have a point-to-point selective soldering with a solder fountain that moves and solders each joint individually, and you're applying flux with an inkjet op or jet fluxer. Again, as I mentioned earlier, the flux is formulated to flow and to fill the barrel. And so it can find its way into places where it wasn't intended to go. And due to the localized nature of the heat source, some flux chemistries rely on exposure to heat to be thermally degraded. So basically, some of the acids in the fluxes require oxidation in order to be rendered inert so that they don't pose a reliability risk. And when I'm giving my talk, I always use a lemon. You can try this test at home. Take a lemon, cut it in half, and lick it, and obviously it's going to be sour. Stick it in the oven for a half hour, take it out and lick it, and it's not sour at all. The heat has transformed the acids in the lemon to where oxidation and thermal exposure has broken the acids down to a much more benign material. Or it's analogous to what we do with the weak organic acids that are used in liquid fluxes. So in a point-to-point soldering operation, if you don't heat it up enough or you're using the wrong flux, you can end up with flux that's not been deactivated and can represent a reliability concern.
You're not suggesting that I use liquid flux in my iced tea, are you?
You could. AIM sells very, very safe fluxes. No, I would not recommend it, Mike. I'm not sure it would be. It'd be very tasty. So those are the areas of the process where you can have issues, but like I said, my reliability concerns with those, if the products are properly selected up front. That's another thing that you need to consider, is that, have I chosen the appropriate flux for the process and the application that I'm using it in? And that always requires a little upfront work. I would consult with the vendors to make sure that I've done my due diligence, that the materials meet all of the constraints that I may have on the production line, and marry that up with what's expected of the product in the field. Okay, so the good part. Now, this is where it gets really interesting. Rework. When we get the call and the customer is experiencing a field failure, and I call the field failure the F word in our industry because that means that it's bad. Something has happened where a product has failed after the customer has received it. Sometimes it happens relatively quickly. Sometimes it can take a long time for the field failure to manifest itself. The first place I look when that call comes in is in any hand soldering or rework application site on that assembly. And I'll use the term rework interchangeably with any hand insertion operation. Normally, if a board's being washed, all the residue should be getting removed. And the reason that something is happening at the workbench is because whatever it is can't go through the wash process, an open switch, or something that can't get wet, or something that can't be exposed to the solvent that's used in the wash process. So it's not necessarily a rework application where you're fixing something. It could just be a hand insertion for something that needs to be installed after the fact. And why I chose to have this conversation with you today was because just this morning I came in, and this is not an uncommon scenario for us, and this happens to me on a weekly basis, where in Asia, this particular customer, the wire solder and flux that is used at the rework bench is not part of the bill of materials for the assembly, which kind of mind-boggling to me. If you consider the following facts, it's the last place that the circuit board gets handled. It is also where there is the highest amount of operator input as it relates to the outcome. It's not a machine. It's not well measured. It's not well calibrated. You're relying on the experience of the operator to use the products that they're supplied properly, which is highly subjective. I mean, there is a lot of things that can go wrong in that process, and that's why we focus on that whenever we have these electrochemical failures. Another thing is, or may not be known, people say I'm building to class 3. Well, no, the joke is I'm building to class 3, but my customer is paying me for class 2. If you're truly building to class 3, IPCJ Standard 01 states that evidence of compatibility between the materials, the fluxes on the board, needs to be evident, needs to be available. So, making sure that the liquid flux that's in the flux cabinet for the wave solder isn't the jug that the operator is grabbing to fill their squeeze bottle on their workbench. That's a no-no. And oftentimes it's that type of lack of understanding of the materials being used that leads to the types of problems that we're asked to address. So I'll look at it from, a risk hierarchy, and starting with the lowest risk first. Generally speaking, the flux core of wire solder is relatively safe in terms of electrochemical reliability. They tend to be high resin products. Resin is a common ingredient in both solder paste, wire solder flux cores, and liquid fluxes for that matter. They are nice, big, stable molecules that don't like to interact with things. And if you don't believe me, try and clean it. I always say that's a pretty good indicator of how stable these molecules are. They don't want to interact with anything, certainly not with moisture and not with aggressive chemistry. They just kind of lay there. The ionic constituents can get entrapped within the matrix of the resin. And if there's no moisture, you need the three legs of the stool for electrochemical migration. You need bias, you need ionics, and humidity. You need water, moisture. Take off one of the legs, no electrochemical, the electrochemical concerns become much lower. So resin, big stable molecule, sits there, relatively inert, doesn't do much. Wire solder contains a lot of resin. We, in fact, have a new wire solder out. We're just releasing it. I released it at Apex for hand soldering. We haven't seen much evolution on the wire solder chemistry front. As I had mentioned at the beginning of the conversation, electrochemical concerns are becoming more prevalent. So we're, in our constant evolution of products, we're looking at this at the rework bench, the place where we see the most issues. So the CX18 is, our next step, our next rev, if you will, of materials for use at the rework bench. So resin out of a wire solder used properly, think about how it actually is. It works. When the soldering iron tip comes down to the workpiece, and of course you're never putting soldering wire onto the iron tip. You're supposed to put it onto the workpiece and then let the heat throw the workpiece, and you put the solder onto the workpiece, and then the heat flows onto the part. What happens is that the flux is a lower melting temperature than the wire. The flux flows out of the flux core over the workpiece. Then the liquidus temperature of the alloy that's in use is eclipsed, and the solder flows chasing the flux and the heat. And so it's very unlikely the cord wire flux will not be deactivated under those circumstances, because you got it hot. It flowed out over the part. It had to melt in order to come out of the wire solder. And then you've got this stuff that consists of a high percentage of resin. It's a pretty safe solder joint. And when I go in and help a customer audit their benchtop process, the first thing I look at is, A, what wire solder is in use. Better be AIM, right? Also, the different chemistries that may be sitting side by side on the workbench. They'll have a water-soluble spool sitting next to a no-clean spool, sitting next to an RMA spool. Everything better be clearly marked, and the work instructions for each job clearly available, because grab the wrong one and you're going to have field failures get out the door without ever having realized it. I remember one of my first calls when I got into this business 25 years ago was to address hundreds of boards that were assembled using water soluble, and it was a well-intentioned purchasing agent that made the decision to buy organic solder because they thought it was better for the environment, not realizing that it was water-soluble flux.
Baptism
all
by
the
flux.
boards that they had built. Yeah, well, it was. I mean, I couldn't not laugh when they said it was better for the environment. I'm like, oh no, and that's not an uncommon scenario. The benchtop is often driven by purchasing, because it's not on the BOM, because it doesn't have a flashing light and need to be programmed and have any real excitement in it. Nobody gets excited about buying a new bottle of flux and buying a new spool of wire solder. They get excited about new printers, new placement, new ovens, new jetters. That's exciting for an engineer. Wire solder isn't all that exciting. But like I said, it's really an area that requires attention. we wire solder, and then there's the flux bottle. And the flux bottle is probably public enemy number one. Operators like the flux bottle because it does two things well. It adds additional activator to the job being performed, which promotes flow, and operators are often judged on speed. And so if you can make it faster, then you're going to make it better. And in that same vein, the solvent that's used in the liquid flux acts as a thermal bridge, so it pulls heat out of the soldering iron tip faster than air does. So it accelerates the soldering process. But as I said earlier about flux blooming beyond the workpiece, it's a localized heat source. And oftentimes you'll see flux, an inch away from where the soldering actually took place. That's a concern for all the reasons that I said before. So what's really important is that a flux is selected that is intended for use in a rework application. We don't want the operators or the engineers using the same flux on the wave solder that they're using on the rework bench unless it's been qualified for use on a rework bench as well as in the wave solder process. Grabbing that bottle can cause a host of issues, and it's probably the number one issue that we see is that it's flux that shouldn't have been used where it's being used or used improperly. Over application of the flux goes back to that problem I said when the operator turns up the fluxer on the wave. Same thing with the operator with the squeeze bottle. You hyperconcentrate these acids. Understand that when we make a product that's 2.5% solids and we do our surface insulation resisting testing on that product, it's at 2.5% solids. If you keep evaporating the flux and you make that into a 5% solid flux, you've doubled the amount of solids present, oftentimes weak organic acids. And if you increase volume of weak organic acid, you decrease the reliability of the assembly because you're increasing the availability of ionic species to interact with moisture and cause electrochemical problems. So that's why very important on the rework bench to make sure that the materials that are in use were intended for the process that they're being used in. And then finally, it's cleaning. So now the operator who has over-applied the flux says, geez, this thing looks terrible, I better clean it. And they reach for a pump bottle with a cotton swab soaked in IPA, and they brush it back and forth, and it looks better than it did before, so it must be clean. And off she goes. The problem with that is that I don't know what that material is now that they have gone after it with alcohol, most often the case. Definitely don't want to use alcohol on the workbench for cleaning operations, even though I'll bet more than half of the cleaning operations that are performed in our industry are performed using IPA. A, it absorbs moisture. B, that cotton swab that I talk about gets put down on a workbench where a water-soluble board was laid down earlier. Water-soluble flux has now contaminated the head of that cotton swab. It's being transferred onto a no-clean board. I mean, you can make yourself crazy thinking about the litany of scenarios where ionic species get transferred onto an assembly at the workbench, whether it's finger oils, a misplaced flux, the wrong flux completely. There's a myriad of scenarios that you can conjure up where ionic species make their way onto the board that leads to these types of failures. But generally speaking, based on my experience, it's usually a half-hearted attempt to try and remove no clean flux residue at the workbench. And so I mentioned the resin earlier, and I mentioned the system of the fluxes being an engineered system and the residue being part of that system to reduce the risk for electrochemical problems. When you partially clean it, when I said I don't know what that is anymore, you've changed the chemical structure of that residue. It isn't what we tested in our lab. It's something else. And I don't know what the electrochemical properties of that something else is anymore. So I can no longer be consultant in that regard. So I would make the case that a partially clean board is a greater reliability risk than no clean flux residue that's been used properly, selected properly, and left in situ. That would be my assessment. May not be acceptable to the person that's looking at that board in that they just see more residue than they're comfortable with. but they need to understand and be educated and trained that that is perfectly acceptable if all of those other benchmarks have been met, compatibility, proper use, etc. So that is the risk of the benchtop, why it should not be ignored by floor supervisors, manufacturing engineers, and process engineers, because it is the number one reason that we get called to try and resolve either field failure issues or residue appearance issues. And just in closing, we're not cleaning chemistry manufacturers. We're flux manufacturers. We work closely with the cleaning chemistry manufacturers, and we develop our products to make sure that our products are cleanable if they are intended to be cleaned. And we even test all of our no cleans for cleanability just to assess where they are on a scale of easy to clean versus hard to clean. So we can formulate a product that we can leave some particularly insoluble constituents out of the formula so that the cleaning guys don't have as tough a time to remove that stuff that's left behind, but understand also that when residue or flux gets heated, it isn't you can't look at the you can't look at the ingredients list of a flux and assess its ability for the flux residue to be removed, because like in cooking, you know, if you took sugar that hasn't been burnt, it'll dissolve in water. If you burn that sugar, it doesn't dissolve in water anymore. I would say flux residue would be analogous to that. Once you heat that flux up, its solubility characteristics change, and it can become significantly more difficult to remove. And the time from application to the time of removal has a big impact on how easy that flux residue is to remove. So there's a lot of things that go into residue, the removal of residue. We usually partner with all the major cleaning manufacturers to get their input, and they often assist us when residue becomes an issue and how do I fix this problem that I have now. That is it. That's my brain dump on rework, the hazards of rework, and how you can reduce those risks.
Tim, at the top you mentioned green and white residues. Now, my understanding is that green residues are consistent with copper chlorides and white residues are consistent with tin chlorides. Is that correct?
They can be. Yes, green is almost always copper. Somehow copper was exposed and it's been reacted with to create copper chlorides. White residues are a little less, they're a little fuzzier, pun intended. They can be. So when tin is reduced by the flux and the oxides are reduced, tin salts, organometallic salts are produced, which are often white. But also white residues can be from the resin. If the resin becomes hydrated, it will often turn white. On a quick and easy test to see if what you've got left there is hydrated resin is to heat it up with like a hot air pencil. And if it goes clear again, and many times it will, you've basically driven the moisture out of it, and you know that it's probably a resin or rosin-based white residue that you've got. Neither of which, by the way, are necessarily reliability issues, but they are aesthetic issues. And the problem with cleaning or attempting to remove residue is if you don't get it right the first time, it's whatever is left behind is really insoluble. So it becomes twice as hard not even 10 times harder to remove whatever is left behind after a poorly executed cleaning attempt. You want to get it all off on the first shot. You get one shot, make sure you get it right. If the residue is left behind, the hammer and chisel is the remedy.
And so it seems that we can dial in on flux as opposed to worrying too much about the paste material itself and whether it was halide-free or not.
Yes and no. There have been studies that have been performed that under low standoff devices, even surface mount, that very safe solder paste, if it's, I want to say just wet, if it's left, not completely processed, it can still represent a reliability concern. So while I would say surface mount is the lowest risk of the process, it's still not without risk. It does have some risk associated with it. And then obviously material selection, the drive to halide free, we like halides as solder manufacturers because they're in very small quantities. They're very effective at reducing metal oxides, which promote soldering. There are a number of characteristics that flux should have to be a good flux, and if probably the number one thing we're called in on, that are solder paste evaluation opportunities is voiding. Halides do a really good job of reducing voiding. So halide-free fluxes tend to be don't have the same characteristics in that performance criteria, and so there's always a trade-off. Anytime I make something safer, I'm typically taking away from the activity profile. Which is it? What do you want to live with? If you're in the Asia market and it's high volume consumer goods, and oftentimes the components condition isn't ideal, halides represent a relatively low reliability risk and promote soldering. If it's a satellite and it's going up into outer space, you may want to consider halide-free products just to make sure that you're taking a belt and suspenders approach, even if you're cleaning the residue off, because chances are you're not cleaning all that residue off. And that's probably a podcast you'll have with one of the cleaning guys about getting underneath those low standoff components.
Yeah. And finally, Tim, would you recommend OEMs specify the rework material used on the bench?
It has to be considered. Like I said, oftentimes it is not even on the radar. I hate to see specifications become so draconian that the manufacturer doesn't have any latitude. And sometimes what we encounter is a material will get specified by the OEM and it's just not available in that region. We don't have a distributor for that product in the United States, and so it becomes really problematic. So I think it's fair to say that if the manufacturer can produce evidence of compatibility between the materials that are in use, that's probably a more practical approach than writing a part number or a particular manufacturer's part number into a specification, because it does burden the supply chain.
Good advice. So that concludes our episode of the Screw Ups. I want to thank Tim O'Neill from AIM for coming on. Our lesson for today is don't overlook your bench. For PCB Chat, I'm Mike Buteau. Have a nice day.